You might have heard this weird fact that there are parts of Canada with less gravity than the rest of the planet. And it's not a myth, it's a real measured phenomenon. There's this massive gravity anomaly basically centered right over Hudson Bay. So let's get into it, because this thing is one of the great puzzles in modern geophysics.
So that's the big question, right? Why? Why does this huge chunk of the Earth seem to be, well, missing some of its gravitational pull? It's not an error in our instruments. There really is a gravity deficit. The real debate is about what's causing it.
Okay, so the most common explanation you'll hear, the one in all the textbooks, points way back in time, thousands of years ago, to the last ice age. The whole idea is that the gravity we're measuring today is actually an echo, you could say a ghost, of a glacier that's long gone.
Now, the key concept behind this is something called glacial rebound. And honestly, it's a pretty straightforward idea. I mean, think about it. You put something incredibly heavy on a surface, it's going to sink down a bit. You take that weight off, and it slowly comes back up. Well, the Earth's crust does the exact same thing, just much, much slower.
So let's just walk through it. First, you get this absolutely colossal ice sheet. We're talking kilometers thick, just sitting on top of Canada. Its sheer weight literally squashes the Earth's crust down into the mantle. Then the ice age ends, and all that ice melts away over thousands of years. But the land doesn't just pop back up like a spring. No, it's a super slow process, and we're actually still in the middle of that rebound today.
So here's the punchline for the conventional theory. Because the land around Hudson Bay hasn't fully bounced back yet, it's still depressed. That means there is literally less rock, less mass in that region than there should be. And we all know from basic physics, right? Less mass equals less gravity. It seems like a perfectly neat and tidy explanation.
But our source material for this explainer takes a very different stance. It argues that when you actually step back and look at the global data, this neat, tidy explanation really starts to unravel.
And this is the central challenge the source poses. I mean, if the Ice Age rebound theory is correct, shouldn't the patterns on our global gravity maps line up perfectly with where all the big ice sheets used to be? Well, let's see if they do. And right away, we hit our first major snag. Over on the left, you've got Canada's gravity low, that blue area, which fits the model perfectly. But then you look at Greenland. It was also covered by a huge ice sheet, yet its southern half shows a gravity high, the red area. That's the exact opposite of what the theory would predict.
And the list of problems just keeps growing. Russia had a massive ice sheet, but there's no big gravity hole there. Northern Greenland does have a gravity low, but wait, the ice is still there, so there hasn't been any rebound. And it gets even weirder. The gravity patterns in Canada don't even match the terrain. You've got mountains in Quebec, which should have more mass, showing low gravity. The puzzle pieces just don't seem to fit.
Maybe the most telling part is this quote our source highlights. It's from the original authors of the theory, Mark Simons and Bradford Hager. Even they admitted, way back in 1997, that there's a poor global correlation between what their model says should be happening and what the gravity maps actually show us.
At the end of the day, even the people who champion the rebound theory are now admitting that, at best, it can only account for maybe 25 to 45% of Canada's giant gravity anomaly. That leaves more than half of this entire mystery completely unexplained.
So if the Ice Age theory is at best incomplete, what's the alternative? Well, the source proposes a totally different model. It's not based on missing mass at all, but on an unseen force, a unified charge field.
Okay, so here's the core idea. The author argues that what we call gravity isn't just one force, but two. You've got the standard gravity field, we all know, pulling things in, but they argue there's also this constant opposing charge field made of photons that's pushing out from the Earth.
So according to this theory, the gravity that we measure and feel every day is already a unified field. It's the net result of that inward pull of gravity minus the outward push of the charge field. What we feel is just what's left over after these two forces have their cosmic tug of war.
Now, this idea completely reframes how we look at those gravity maps. The red areas, the gravity highs, they aren't just places with more mass. They are dense regions like mountain ranges or thick parts of tectonic plates that actually block that upward flow of charge. With less charge pushing out, the net inward pull of gravity feels stronger. And the blue areas? Well, those are regions where the crust is thin, allowing charge to flow out easily, which offsets gravity more and gives us a measured gravity low.
And suddenly, this simple model seems to explain all these major global features so elegantly. Mountain ranges and the thick seams where tectonic plates grind together, they're dense. They block charge, so we see a gravity high. But the centers of those same plates are thinner. Charge flows through easily, and so we see a gravity low. The pattern becomes really consistent all across the globe.
Which brings us right back to our original puzzle. With this alternative theory, Canada's gravity deficit has nothing to do with Ice Age ghosts. It's simply the result of charge flowing easily up through the thin, stable center of the North American tectonic plate. The hole isn't missing mass, it's an open channel for charge.
But, the source material doesn't just stop with a new physics theory. It goes a step further and raises a broader and I'd say more provocative question about how science gets presented to all of us. The author's real concern is about popular media, TV shows, that present the glacial rebound theory not just as a leading idea, but as settled fact. The argument is that when a major outlet just declares that the problem is solved, they're not really doing science education anymore. They're doing something else entirely.
And here's the core of that concern. Science is supposed to be an adversarial process, right? It needs debate, it needs criticism, it needs the fair consideration of opposing ideas to move forward. So when one single theory is sold to the public as the final answer, especially a theory with known problems, it basically short-circuits that entire process. It shuts down the conversation.
And that's the final, really challenging thought this explainer leaves us with. It's a question that goes way beyond gravity maps and tectonic plates. It asks us to think critically about how we learn, what we're told is fact, and what it really means to be part of the scientific process. Definitely a question worth thinking about.